Hello guys, welcome once more to another video in our YouTube channel. So in this video we are going to be looking at equation on rotational dynamics that came in June 2003 for the math paper 3. I can't remember the equation because the equation was just sent to me by a student who was facing difficulties in solving. Anyways, in this video I'm not going to solve the equation completely because it's going to be a little bit lengthy. So basically I'm going to solve just the first part of the equation, which is asking us to prove that 7a d theta on dt all squared is equal to 5g sine theta. In the other videos I'm going to now do the second and the third part. Okay, so just to make the video a little bit shorter and easy to watch, so let's get started. Alright, so the question reads: a uniform rod of length 3a and mass m carries a particle p of mass 2m at one end, and the other end is smoothly pivoted on a horizontal axis. The rod is held horizontally and is then released. So we need to prove that the equation of motion of this rotating body, and the body here is a combination of a rod and a disc, a combination of a rod and a particle. We need to prove that its equation is 7a d theta on dt all squared equal to 5g sine theta, where theta is the angular displacement, that is the angle that the rod makes with the horizontal. It has been specified that it's an acute angle. It means that it's less than 90 degrees. So whenever you're faced with problems in rotational dynamics, it is always preferable to start by drawing your diagram. Once you draw your diagram and it is correct, then you start analyzing the problem. So we start by drawing the axis because we are basically going to always get the moment of inertia of the system, and the moment of inertia of the system is always gotten about an axis. So once your axis is wrong, then you are off track. So they told us that the axis is horizontal. All right, so because they said that we have a rod, for example, carrying a mass m at one end, and then now the other end of the rod is now pivoted on a horizontal axis, and then initially the rod is held horizontally and then it is now released. So we have the horizontal axis, we have the rod, and for the characteristics, the mass of the rod is small m, and then the length of the rod is basically 3a. Now we now need to choose the end. All right, because you could choose any end of the rod and attach the particle to it. So I can choose the right end of the rod. I attach a particle whose mass is 2m. So it means that the rod is now hinged on this other end about this smooth horizontal axis, initially in the horizontal position, and then it is released. So after a certain time t, what happens is that the rod is now in this position. Like I said, the angle theta is the angular displacement, and it is an acute angle, so it is less than 90 degrees. So it means that the rod will definitely be in this position, okay, when it is released. So we have rotating in this direction. Omega is the angular velocity, that is change in angular displacement with respect to time. So the angular displacement is theta, the angle that the rod makes with the horizontal. So this is what we have. So to be able to prove this, we must use the principle of conservation of mechanical energy, and that principle says that the initial mechanical energy of a system is equal to the final mechanical energy. But knowing that mechanical energy is a sum of the kinetic and potential energies, we can just find the initial values of the kinetic and potential energies and we sum, as well as to find the final values and sum, and then we equate the two together according to the law. So the mechanical energy initial is the Ke initial plus the Pe initial. Our Ke is basically half times the moment of inertia times omega squared. I derived it in the very first video of rotational dynamics. If you're new to this channel and you have not watched that video, make sure you check out the video in this channel. The title of the video is Rotational Dynamics 1. You can check the playlist or you check the description of this video you're watching. I'm going to indicate the link there. All right, so kinetic energy, we derived it as basically half times the moment of inertia of the system times the square of the angular velocity. But since initially it was not rotating, then the angular velocity is 0. That's why the kinetic energy is 0. Now potential energy is mgh, and h there is a distance from the center of mass of the system to the line of zero potential energy. Our line of zero potential energy is basically our horizontal axis, and the center of mass of this system initially is basically on the rod. Okay, it's basically on the rod, and since if you are on the rod, then you are basically on the axis, on the line of zero potential energy, then there is no distance between you and the line of zero potential energy, because the rod is basically parallel. In fact, the rod is on the line of zero potential energy, so there is no distance separating them. That is why the initial potential energy is zero. So when we add the two, we get that the mechanical energy initially is equal to zero. Now we need to find the final mechanical energy, which is the sum of the final kinetic and the final potential energies. So what is the kinetic energy? Like we said, it is half times the moment of inertia of the system, is, times the square of the angular velocity. What about the final potential energy? It is the mass of the system times the acceleration due to gravity times h. Like I explained, this h here is basically the distance from the center of mass of the body or of the system to the line of zero potential energy. So like I said, omega is simply theta dot. Theta dot, the dot there means that we are differentiating theta with respect to time. So I've just replaced omega with theta dot there. Now we need to square it. All right, so the objective now is to get the value of h and also to get the moment of inertia of the system, because according to the proof, d theta by dt is basically theta dot. Okay, so if we equate these two values, you realize that the only missing terms are what? The moment of inertia of the system, the value of h. The mass of the system is basically adding the mass of the rod and the mass of the particle, which is 2m plus m, which is going to give us 3m. So the only two missing terms here we need is h, which is a distance from the center of mass of the system to the line of zero potential energy, and I of s, which is the moment of inertia of the system about the horizontal axis. So clearly we are going to indicate h on the diagram. What you find here is basically the center of mass of the system. Okay, now there's something very peculiar about this system. If this system was just a rod, was just made up of a rod, then the center of mass of the system is going to lie at the center of the rod. Okay, in fact, for plane figures, the center of mass, for plane uniform figures, the center of mass of that figure lies at its center. But now this is basically a rod particle system, so the center of mass will never lie at the center. We will need to get the position of the center of mass. Okay, so I've just indicated that maybe the center of mass of the system is at this point, and we said that h here is a distance from that center of mass to the line of zero potential energy. So we need to get the distance from this dot here to the line of zero potential energy, and you clearly see that that distance is going to be in function of theta. But to get that distance, okay, if I use sine of theta is going to give me the opposite, which is h, divided by the hypotenuse. What is the hypotenuse? The hypotenuse is a distance from the center of mass of the system to the other end of the rod that was hinged. So if we are able to get that distance, then we are good to go. So how are we going to get that distance? We are going to apply the principle of conservation of moment, which says that clockwise moment equal to anti-clockwise moment, or basically it says that the moment of a system, that's the moment of a whole system, is equal to the sum of the moments of the individual bodies that make up the system about the given axis. The axis here is a horizontal axis. Okay, so what is moment? Is a force times the perpendicular distance from the given axis. So my given axis is horizontal. So for me to apply that principle, I'm going to find the moments of the individual bodies about that given axis. In fact, we can say that the axis here is basically this line that I am indicating with a laser. Okay, that is about this end of the rod. That's our pivot, kind of, not necessarily about the axis, about this pivot, because we need the distance from this end of the rod to the center of mass of the system. So we basically need to take the moment about this other end of the rod, which is not containing a particle. All right, so we basically have that. We take the individual bodies that make up the system. What are the individual bodies? We have we first of all have the rod itself. Okay, the rod itself. Now what is the weight? Because we need to take the force times perpendicular distance from the pivot. The pivot is basically this end of the rod. Okay, so the force, the force this time around is basically the weight, and the weight of a body is the product of its mass and the acceleration due to gravity. So if we begin with the rod, which is the first component in the system, we are going to have the mass of the rod is m, and then the acceleration due to gravity is g, so the weight is m times g. Now this 3/2 here is basically the distance from the center of mass of this rod from the line of 0 from one of the ends of the rod. Okay, because we need to find the weight of the rod is acting at its center. That is why we are taking the weight of the rod times the distance that is separating one of the ends of the rod to where the weight is acting. So we have m times g for the weight of the rod, and the length of the rod was 3a. So it is clear that the distance from the center of the rod to this other end is 3a divided by 2. Now let us now go to this particle which was attached to this other end of the rod. The weight of the particle is 2 mg. I forgot a g, so we need to attach a g to it. It's 2 mg. Okay, the weight of that particle is 2 mg, and then the distance that is separating this particle from this end of the rod is basically the length of the rod, which is 3a. The center of mass of the particle is at the center. In fact, the particle is too small because it is a point mass. Okay, so it is not like a disc or whatsoever. So basically the distance separating the center of mass of this particle and the other end of the rod is basically the length of the rod, which is 3a. Now we need to equate it to the moment of the whole system, which is basically the weight of the whole system times the distance separating this end of the rod from the center of mass of the whole system. That distance is a distance that we are finding. We call that distance d. The weight of the rod is basically the weight of the system is basically the mass of the system, which is the sum of the mass of the rod and that of the particle, that is m plus 2m, then times g. This d here is what? The distance separating the center of mass of the system from this other end of the rod. All right, so make sure you go through this particular explanation again to be able to get the concept behind this. All right, so from there we just have to simplify. Okay, we simplify. The mg's cancel all through. If we simplify the left hand side, this is 3a on 2, okay, plus 2 times 3 is 6. So 3a on 2 plus 6 gives us 15a on 2. Now the m and the g cancel, so we basically have 3 times d, because m plus m is 3m. Okay, so we have 3d. So if we get the value of d, d is going to give us 5 divided by 2a. So this d here is basically the distance from the center of mass of the system from the other end of the rod, because they said the rod was smoothly pivoted on the horizontal axis. All right, so that is a pivot. That's what we are talking about. All right, so that distance here, the distance from where the rod was pivoted to the center of mass of the system, is 5a divided by 2. All right, so how do I now get h? I need to use the sine of theta. The sine of theta is the opposite, which is h, divided by the hypotenuse, which is 5a divided by 2. So it therefore means that my h becomes 5a divided by 2, the sine of theta. So I can now get the final potential energy. The final potential energy is basically the mass of the system times g times h. The mass of the system is 3m, we saw it already, and my g is g. Now what about my h? Is 5/2 times sine theta. But this negative sign here is because h is basically a distance that is below the line of zero potential energy. So h is actually displacement, okay, and displacement has magnitude and direction. So since it is below the line of zero potential energy, then we need to attach the negative sign to it. So this is my final potential energy. Now what is left is to get the moments of inertia of the system. And this system is a combination of the rod and a point mass, that's a particle. So the moment of inertia of the system is basically about the horizontal axis. Okay, it's basically gotten by summing the moments of inertia of the rod about that axis plus the moment of inertia of the particle about that axis. Okay, so how do I get the moment of inertia of the rod about the axis? Now, the moment of inertia of the rod, okay, about the axis. Now we need to know how the axis is placed. Let me just tell you, IR is the moment of inertia of the rod, okay, and the axis is basically passing through one of the ends of the rod. Is it okay? Because basically you can see this way, this horizontal here, that was in the initial case, okay, it was a horizontal axis, but now the rod, according to the equation, the other end of the rod is smoothly pivoted on a horizontal axis. So basically, for this system, okay, for this system to actually be rotating in a vertical plane, then this axis must be perpendicular to the rod. All right, the axis must be perpendicular to the rod. So the axis being perpendicular to the rod, we basically have that the axis is passing through one of the ends of the rod, and the axis passing through one of the ends of the rod, you are going to get the moment of inertia as m r l r squared divided by 3. All right, so you can check your formula booklet to be sure about this. Okay, so the moment of inertia of a rod about an axis passing through one of the ends and perpendicular to the plane of the rod is the mass of the rod times the length of the rod squared divided by 3. Now what about the moment of inertia of the particle about that axis? So I've read the equation again, and it's kind of a little bit confusing if you are not very vigilant concerning this axis. Okay, you should note that the equation says that the rod is held horizontally and it is then released. But now, how is the axis? According to the equation, we have that the other end of the rod is smoothly pivoted on a horizontal axis. Okay, but now when the rod is rotating, because it was held horizontally and now released, so if the rod is held horizontally, what does it mean? It means that the axis is basically vertical. Okay, so when the rod is held horizontally, then the axis is kind of vertical. So that's why in fact what is here is just the axis. So this end here is my axis where it is pivoted. So when the rod is held horizontally, the axis is vertical. All right, so back to the moment of inertia of the particle about that axis. Basically, by the definition of moment of inertia of a point mass, we just need to take the product of the mass and the square of the distance separating the mass and the axis. The distance separating the mass and the axis is the length of the rod. That's why I put the length of the rod squared. Okay, so when we simplify, the mass of the rod is m, the length of the rod is 3a all squared, we divide by 3. Then we add to the mass of the particle 2m, and the length of the rod all squared is 3a all squared. So if we simplify correctly, we get that the moment of inertia of the system about that axis is 21 ma squared. Okay, now we need to apply the principle of conservation of mechanical energy, which says that the initial mechanical energy, which is 0, is equal to what? Equal to the final. What is the final? We just replace is with 21. You replace theta dot yes with theta dot. We replace the final potential energy. If you multiply 3 and 5, you get 15. There is a negative sign, that's why you find a negative sign here. We have 15 mga on 2 sine theta. So all the m's cancel, okay, and then we can even divide all through by a, so that a squared on a will just give us a. 0 on a will give us 0, since a is a positive, since a is a constant different from 0, because it is in form, it is kind of varying. Okay, the length of the rod cannot be 0, so that's why a cannot be 0. So this means that we have 21 a squared times theta dot equal to 15 g sine theta. I omitted an a, we need to attach a certain a to it, so let me just put the a here, and one of the a's is going to cancel, and when it cancels, we just get we divide all through by 3. We are going to have 7a theta dot square to be equal to 5g sine theta, which gives us a proof. 7a d theta on dt all squared equal to 5g the sine of theta. So guys, see you guys in the next video. So in the next video, like I said, I'm going to be doing the other two parts of the equation. Make sure you share the video with your friends. If you have a problem in understanding, make sure you check the video links to other videos in this topic so that you can go through. Most of you have been getting to me on WhatsApp for the PDF notes, and I just told you guys to wait, okay, because I'm very sure that the video you watch me telling you to get to me for the PDF notes, the video was, I think, done 2 years ago, so basically I can't find those notes again. So but I'm almost done with what I'm preparing. That's why I told you guys to wait. So for those of you who need the notes, you can get to me through WhatsApp on the contact on your screen. Latest by Monday, I'm going to be done with the notes. All right, so if you got to me already, make sure you remind me so that I send you the notes. Thank you guys for watching, and thanks for sharing as well.